Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are looking at the course Introductory Transport Phenomena based on the textbook by Welty, Rohrer, and Foster. We are using the 7th edition. In this lesson, we are beginning our study of Chapter 2 on fluid statics, and we're looking at Section 2.1, Pressure Variation in a Static Fluid. By way of introduction, I'd like to define hydrostatics for you. Hydrofluid statics at rest, or static, right? So we're studying the study of fluids at rest. But we know that a fluid is never truly at rest, right? I mean, if the fluid is on Earth, it's moving through space, right? So what do we mean by at rest? And in this case, we are saying that the inertia is zero relative to the Earth or whatever other frame of reference we are using. That means that you're only going to have pressure forces and gravitational forces. So let's consider the forces acting on a small element. We're going to begin by looking at a small element of volume delta x, delta y, delta z. The net force is going to be due to the pressure on each face and the weight of the element. Let's start with the weight of the element. That's probably the easiest. So we'll take the density times the gravitational acceleration times the volume, delta x, delta y, delta z. And then we want to look at the pressure on each face. So we have one oriented parallel to the x-axis, one parallel to the y-axis, and the z-axis. So if we look at those, there's going to be one that's at point x and one that then is x plus delta x away, or the two facing sides, and those pressures will be in opposite directions to each other. They are acting in the x direction. So that's going to be the E sub x direction. And the size of that face is going to be delta y, delta z. And I can do this for each of the others. My E sub y component, length delta x, delta z. And finally, in the z direction, EZ delta x delta y. And this sum of forces is going to equal to 0. Once we do a balance like this over a specific size, even though it's a tiny size, I still want to next, as my first step, divide through by that elemental volume's size. So I'm going to divide by delta x, delta y, delta z. Every term will get divided by that. And so we're left with just the rho g, the delta p in the x direction over delta x times the unit vector ex, py minus py plus delta y over delta y ey, and then the same for the pressures in the z over delta z times ez. Now, if I let the volume approach 0, let it shrink down to nothing, and recognize that these derivatives are almost the definition of the derivative, but the signs are switched, right? F of x plus delta x minus f of x over delta x is the definition of a derivative. So this means I have a whole bunch of these derivatives, but they're the signs are negatives, right? So I'm going to rearrange this at the same time I do this limit so that I get rho g is equal to dp dx times the unit vector in the x direction plus dp dy, unit vector in the y direction, plus dp dz times the unit vector in the z direction. Now this may look familiar to you from your Calculus 3. If not, this is a new opportunity to learn it. But this really should look a lot to you like the del operator. So this is the del operator operating on the variable p. Del being d dx in the x direction, d dy in the y direction, and d dz in the z direction. And so therefore what we have come up with is that rho g is equal to del of p. Well, rho g really is a vector quantity. G is a vector, and the del is a vector, so this is a vector equation. Normally we say that g is acting in the z direction. Now that's an arbitrary assumption that we've made, but if we use that as our standard, then we can break this up into the various components in the x direction, the y direction, and the z direction. In this case, in the x direction, we have dp dx equals 0. In the y direction, we have dp dy equal to 0. And finally, in the z direction, dp dz is equal to rho g, the gravitational acceleration component. Now, sometimes you will see this written using the gamma symbol. That is simply rho times g. It is just another term variable sometimes you will see. So let's look at the integral of just this last piece. The other ones are not very interesting. Let's integrate this from a height of 0 to an arbitrary location h. So in this case, dp dz is going to be delta p is equal to, well, 0 to h of rho g dz. And if those are all constant, then this is just rho g z from 0 to h, or rho g h. Okay? So this is the pressure change that you would get over a height change. And if you have a known starting value, so if maybe it doesn't start with a pressure of 0, okay, then the P is going to be that starting value plus rho GH, right? This is going to be like really an important relationship that we're going to jump in and just write often, okay? It's very useful to have. A lot of times this P naught is going to actually be the atmospheric pressure, but it doesn't have to be. So it's the atmospheric pressure or some known value of pressure at a point. So let's begin by looking at manometers as a way of applying this definition that P is P naught plus rho GH. A manometer is a very, very simple way of measuring pressure. You can build yourself a manometer right now. A manometer is a fluid-filled tube, and within a given fluid at a given height, the pressure will be the same at that height anywhere in the fluid. And so we can use delta P equals rho GH to determine the pressure in a system. Now, when you change fluids, it's going to change because, remember, it's rho GH. And so, therefore, that height change is going to be different because on this side you have one density and on this side you have a second density. And so, whereas at this point the pressures are all the same, we can call that P naught. The pressure here and here are not the same because there are different fluids in there. And the way we're going to use this is that we can simply look at the pressure at one side is going to be the pressure on the other side plus rho g times this delta H that we are observing in the difference in the height of the two legs. So let's look at an example. In this case, we have a tank of gas. It is containing a fluid of density 0.1 pound mass per cubic foot. So gases are going to have small densities like that. It is connected to a U-tube manometer. So notice the shape of this makes sort of a U. And the manometer contains water. Okay? The open side of this is open to the atmosphere. So on the right side, it's open to the atmosphere. On the left side, it's connected to the tank. We want, okay, well, and it contains water, so the density is 62.4 pounds per cubic foot. We want to know what is the pressure inside the tank. So for a gas, it's going to be the same pressure at any point. We don't really worry too much about the height difference on gases. It's not 100% true. Yes, there is a little bit, but look at the differences in these densities. Gases have very small densities, and so the pressure is going to be fairly constant throughout unless you have large height differences. Water, on the other hand, is fairly heavy, and so those pressure differences with height, they're going to make a difference. Now, what we have here, given information, is that we have at this point here, the center point of our tank, the gas is pushing down on the water, and it's pushed it down half a foot. And then there is a U, and the bottom of the U is 1 foot below that. On the right side, the water has been pushed up so that it is 2.5 feet above that 1 foot drop. So from here, this height is 2.5 foot to the open to the atmosphere part to the point that is in common on both sides. Okay. What we want to do is figure out the pressure in this. Let's designate this as P sub T for P for the tank. So the pressure for the tank, if I were to just go a little step by step, I can look first at this little piece here, this gas. So between here and this point, I've got it acting in the downward direction, right? It's pushed down. It's the weight of the gas, so rho for the gas times G, and the distance is 1/2 foot. Okay. I next have this liquid height here. Again, it's going down, so that's P for the liquid times G. Gravitational acceleration is the same, and that is a 1 foot height. This has no height difference, so I can skip over that, and let's now come up here. So this is now acting up. So rho for the liquid times G, and again times 1 foot. Now, it doesn't take too much paying attention to see that those were the same, and maybe that was a silly step to have included. But let's now go to our next step. So I have this, which is 2.5 feet. It is acting up. It's the rho for the liquid times G times 2.5 feet. And at that point, I have the known pressure, the atmospheric pressure. So at this point, we have this expression here that I can solve for the pressure in the tank. And I'm just going to plug in numbers. Rho for the gas is 0.1 pound mass per cubic foot, and for the liquid is 62.4 pounds mass per cubic foot. I've pulled the G out, and we'll deal with that in a moment, but I want us to just look at the relative numbers here. This first one is negative 0.005 pounds mass per square foot, and this other one is 156 pounds mass per square foot. And I wanted to do this because this one is very small compared to this one. And it really wouldn't have even mattered if I had like doubled the size of the leg, right? It still would be very small because it's a gas, okay? So there's just not a lot of pressure change in a gas. And I wanted you to see that so that you can be aware of it and make some simplifications in your own work in the future. Okay, so if I do this, then this is really 156 pounds mass per foot squared. And what is G? Well, we're in English units or American engineering units, so it's 32.2 feet per second squared. Okay. And now I need a G sub C. So 1 pound force second squared is 32.174. There's a point right there. Pounds mass foot. And this is okay, except for it's going to get you pounds per square foot. And the usual units are pounds per square inch. So we need one last conversion factor. 1 square foot is 144 square inches. And so the pressure in the tank is 1.0833 pounds per inch squared, plus the atmospheric. This is 1.0833. The way we normally write this is PSI for pounds per square inch. And this is the gauge pressure. If I add atmospheric pressure, it's going to become absolute. And if we say that that was, say, 14.7, then this would be 15.783 PSIA. Absolute gauge. Okay, so A at the end means absolute. G at the end means gauge. So I'd like to look at just some observations from this. First, the part of the U that's filled with the same fluid cancels out. So usually we just kind of set the zero height as the lowest interface and ignore everything below that. You don't have to, but you're going to end up with things that cancel out, and so it seems sort of silly. Second, the density of the gas was so much smaller than that of the liquid, and so often we neglect that part. Don't even bother writing it down, okay? In that case, the error, if you used it or didn't use it, it's 0.0003 psi. We're talking about something that was much larger than that. Again, we wouldn't notice that. You're going to always, whether you're using American engineering or whether you're using SI or whatever units you choose to use, you're going to need G sub C to convert mass from the density to a force. As far as our units, pressure units, usually in SI we'll use Pascal or kilopascal is very typical. There you need to know that 1 Pascal is a Newton per square meter. And we use PSI in American engineering. So a PSI stands for pounds force per inch squared. If you don't include the atmospheric pressure, you have gauge pressure. If you include the absolute or the atmospheric pressure, you have absolute pressure. And I apologize for this funny typo there. That's supposed to be a subscript S, P sub abs. When we have American engineering units, probably the only nice thing about American engineering units is that it absolutely indicates for us whether or not we are talking about gauge pressure or absolute pressure, because we add that to the PSI. So PSIG is pounds per square inch gauge pressure. PSIA is pounds per square inch absolute pressure. So how would one measure atmospheric pressure? A barometer is the basic device used for measuring atmospheric pressure. It really is a manometer, but it is made in such a way that it has a sealed end, okay, that is going to have a vacuum in it, okay? It's open to the atmosphere on the other side. Therefore, one pressure is 0, the vacuum, and the other side is going to be our air pressure. So therefore, all I have to do is read the rho GH in order to get the pressure. Now, because of the heights involved with this, we usually end up using mercury as the fluid, because if we were to use water, we would require, for just typical atmospheric pressure, a column of water that was 34 feet tall. That's going to be a little awkward to be running up and down to read. And so if we switch to mercury, a very heavy fluid, the height is only 30 inches. And so that's much more rational. And so mercury is the most common barometer fluid used. Now, there are more modern ways of measuring this. That's going to be in another course for you in the future. But for now, this is the original way, the very most basic way of measuring atmospheric pressure. So what is standard atmospheric pressure? Obviously, it's changing all the time, because if you watch a weather forecast, they'll tell you the atmospheric pressure right now is, okay? But there are some standard values that we use. 1 atmosphere is the standard. 1 atmosphere is 101.325 kilopascals, or 101,325 pascals. We also use bars. That 1 atmosphere is 1.01325 bar. If you're in millimeters of mercury, 1 atmosphere is 760 millimeters of mercury. It's also sometimes called the torr, after Torricelli, the gentleman who did work in this area. In PSI, 1 atmosphere is 14.696 PSI, pounds per square inch. And if you are using inches, okay, 29.92 inches of mercury, or if you want water, 33.9 feet of water. Now, we do know that atmospheric pressure changes with the weather. It also changes with altitude. If you have something where maybe you're working at something far from sea level, up in, the mountains, Appendix G is going to list standard atmospheric pressure as a function of altitude, and that can be quite useful also. One last thing I want to do is look at the relationship between pressure and density. So we were talking about density being constant in what we get. What if it's not constant? Okay, so in that z direction, we said that dp dz is equal to negative rho g. Well, if I have a gas, we have dp dz is equal to, the density is for an ideal gas, negative P times the molecular weight over RT. And now I can do separation of variables. dP over P is equal to negative mg over RT dz. So now let's integrate from a starting point at z equal to 0, where we'll say that P is atmospheric pressure, to a second point, point 2, with an arbitrary z and then therefore a P that corresponds to that. In this case, we end up with the natural log of P going from P to P atmospheric, whichever way, it doesn't really matter, is equal to negative mg over RT, none of those vary with z, times z going from, let's see, P, there we go, just get those two so that they are the same. And if we can play various algebra games with this, but log of P over P atmosphere is negative mgz over RT. The P is atmospheric pressure times the exponential of negative mgz over RT. So for an ideal gas, we can see how density would change with the pressure. This concludes this material for section 2.1. I thank you very much for your time. We will next be looking at forces on submerged surfaces.